Assalamu alaikum students. So as I have mentioned earlier that I will be recording the lectures which you will be missing during the midterm exam period. So this is the first video from them, and this is about the topic is about volume studies, and we have covered a little bit about this topic in the previous chapters as well, but now we are focusing on how to collect volume and what are the procedures to do volume studies, and then what are the calculations we can do with the volume data. So this is from chapter 10 of the textbook. Let us begin. So there are certain parameters which are related to volume which are important for traffic engineering analysis and traffic engineering design. Okay, so basically when you are doing the design of any transportation facility, you want the existing volume on the facility, the existing demand of the facility, and the projected volume for future. Okay, so this facility is supposed to last for 20 years, then what will be the demand after 20 years? And one more thing which you need is what are the peak hours in the day, like where do they exist, okay, and what times they exist, okay, and how long is the peak period. Okay, in certain cases it can be more than 1 hour as well, so that's why you see the term peak hours. Now the term which are related to volume, we have discussed them earlier as well, include the volume itself, which is the actual number of vehicles passing through the highway in an hour. So in this chapter we will be talking about volume in terms of hours. Then we have rate of flow, which is the flow value converted to equivalent hourly volume. So if you have 15 minutes of flow, then you multiply by 4, you get the rate of flow that will become per hour. Then you have the demand, which is the number of people who want to pass through the highway in an hour. And then we have the capacity, the maximum number of vehicles that can pass through the highway in an hour. Okay, all these terms can be in vehicles per hour, or they can be passenger cars per hour as well. And we will discuss this term passenger cars per hour and how do we get it in the next chapter. And one more thing is you can divide the volume or rate of flow or demand or capacity further by the number of lanes, so you can get vehicles per hour per lane or passenger cars per hour per lane as well. There are certain important characteristics related to volume. Volume is dependent upon demand basically. When demand increases, volume is supposed to increase, and demand varies in different scales. So demand can vary during different times of the day as well. So you may have more people going towards offices in the morning time, and then you may have more people coming towards their home in the evening time. So demand can reverse in different times of the day. It can change in different days of the week as well. So demand for a particular area may be very low on weekends as compared to weekdays, and vice versa for some other locations. For example, shopping complexes, okay, or picnic places, they may have high demand on weekends as compared to weekdays. And demand can vary in different months or seasons of the year as well. And we observed it in a study which we did in Bahrain in I think 2019. And that study basically we were trying to gather the data related to tourists or people who come to city centers and these famous places in Bahrain. And what we found was there were very low number of people at that time because it was summer in those places. Okay, so this is an example of demand varying in different months or season. Then demand can vary according to some events as well, and these events can be planned or unplanned. For example, in Bahrain we have Formula 1 and we have National Day events. These are planned events, and you can see that it changes the demand completely. If any one of you has driven or has experienced the congestion we have on certain roads during the National Day events, you get my point there. Okay, and these events can be unplanned as well. For example, the natural events, for example, heavy rain, we don't have that, but we have sandstorms. Okay, and in certain countries you have fog as well. So these are unplanned events, and they can also change the demand pattern, because obviously people then may not want to travel in those weather conditions, or some incident can happen and can also change the demand. So demand varies in different ways and in different time scales, so we need to have a close eye on the demand. So working on that particular concept, we have developed intelligent transportation systems. What are intelligent transportation systems? These are basically monitoring systems which are intelligent enough to convey the information, and if need be they can take decisions on your basis as well. Let me give you a very small example of signals, traffic signals. Traffic signals are in many countries they are operated with some intelligent system attached to it, some sensors attached to it. So these sensors basically record traffic data, and then they cause the signals to change their timings according to the volume which they are observing in different directions. So the system is recording the data and is changing the signal timing as well. So this is why we call it intelligent. Okay, and obviously this data is transferred to the control centers as well, or to the authorities which are collecting traffic data as well. So this data can include information about different routes, which routes have construction work, which routes have accidents, which routes have congestion, travel times on different routes. If you go online, there are apps available for certain highways and certain corridors. For example, there's an app available for King Fahd Causeway. So if you select the time and the day, it will tell you how much will be your average travel time on the causeway. Okay, and this information can be directly communicated to the drivers as well. I have seen in Pakistan there are radio programs which broadcast this information that this road is closed, don't go by this road. Okay, and in Western countries they have these electronic signboards. So these signboards tell you that there is congestion ahead. I have seen one in Belgium as well. I have seen some pictures and videos which are for USA. So these are all part of intelligent transportation systems. Now in these coming slides, I will discuss a little bit about the change in trends in volume and what are the important characteristics about it. And there are some graphs. I will highlight some points, but if you look at the graph, maybe you are you may see some more important features as well. Okay, so don't rely on what I'm saying. Okay, so these are three graphs which are showing traffic variation on different days of the week. So you see different lines in each graph, one representing Wednesday, which is a weekday, another representing Saturday, another representing Sunday. Okay, and then on the x-axis you have the time of the day, on the y-axis you have the percentage of daily traffic, okay, coming in that hour. So this graph is basically showing you the peak hours. So the hour which has higher percentage of daily traffic, which becomes a peak hour. So we have the peak hour for all the graphs here in this region, which is between 3 and 5 p.m. Okay, and it is for all the days. Okay, and then you can see that trend of traffic is almost the same. Okay, it is almost the same for all, like, different days of the week as well. Okay, but these are three different highways. This is a local route, maybe in a residential area or something. This is going to a recreational site, a picnic point, a beach maybe, and this is an intercity route, which means basically going from one city to another city. Okay, so one thing which you can see is when we have a local route, then we have basically this peak is more prominent than other graphs. Here in this graph for the intercity route, there is only one prominent peak. Okay, but in the other two you can see another peak as well, very small peak, but this is more prominent for the local route. The local route experiences two peak hours, one in the morning, one in the evening. Okay, but for recreational routes, that the timing for going is not generally fixed. Okay, we have a peak hour in the morning, peak hour in the evening, but traffic is distributed generally in the other hours of the day. And then you can see if you have a recreational route, then weekends have higher traffic. If you have a local route, then weekday has higher traffic. Okay, and similar here. Okay, but it's not so prominent here. It's not very clear here which day has higher traffic than the other. Okay, now this is showing a flow for 4 different sites. Okay, these are different types of sites, and flow are again shown for different hours of the day. Okay, and then you can see now this site has a very prominent peak, this side has two peaks. Okay, and this side again has a very similar trend of traffic throughout the day, this one as well. So the one which has a very prominent peak, it seems like maybe a recreation route or an intercity route or something. These other sites 2 to 4, they may belong to urban areas. Urban areas traffic normally remains up to a certain level for most of the hours of the day, because in urban areas you have many businesses going on throughout the day. People are going to offices, schools, hospitals, so many things are open, so a lot of traffic, and this traffic does not die down for most of the hours of the day. It remains at a very high level. So this is what you can see for site 2, 3 and 4. Now you can see 3 lines here. These 3 lines are basically showing the range of traffic. So they have collected traffic data for different days. Okay, so this is the average for this hour of the day, and then this is the range for this hour of the day. Okay, and you can see that the range can vary like around 200 vehicles per hour. For each case you can see there is a difference of around 200 vehicles per hour. So this is a normal variation which you can have between different days of the week, or between different days on the same site. Okay, for the same, if you consider same day and same site, then you can have a variation of around 200 vehicles per hour in the traffic volume. Okay, if nothing changes. Then this is a figure which is showing you the variation in peak hour traffic. So on the x-axis I have the hour of the year, and on the y-axis I have the percentage of ADT in that hour. So ADT means the average traffic of the entire day for the whole year. So you have collected traffic data for 365 days, and then you take the average of 365 days. This will become your ADT. You have discussed it earlier as well. And then you calculate the percentage of hourly traffic with respect to ADT. Okay, so for example ADT is 2000. Okay, or let us assume a higher number. ADT is, let's say, 40,000. So in a particular hour of the day you observe 2000. Okay, so percentage of ADT will be basically 2000 upon 40,000. Okay, so obviously in one day you have 24 hours, and then in 1 year you will have 24 into 365 hours. Okay, so they are like thousands of hours in 1 year. So you have collected data for the entire year, for each day and for each hour in the year, and then for each hour of the year you have calculated this percentage, and this is a percentage which you are plotting on the y-axis. On the x-axis, once you calculate this percentage, then you order the hours in terms of their percentages. So the hour which has the highest percentage of ADT coming in that will go at the top place. It will become hour number 1. Okay, and the second highest percentage will become hour number 2, and third highest will become hour number 3, and so on. So the lowest will become the last hour of the year. Okay, so for each hour you calculate this percentage. This is a volume in that hour, and this is your AADT. Okay, so you calculate this percentage, you arrange the hours, and you plot them here. Okay, now what is this showing? You can see each type of highway has a slightly different shape than the other. Okay, so for example, urban radial, urban circumferential routes have almost a straight line. Okay, and when you consider recreation or rural routes, then they have a peak at the start, and then they tend to go straight as well. They are almost straight. You can see in this portion they are almost straight. Okay, So this is so in the when you go down the hours of the year, like the hours which have lower percentage, then all types of highways have almost the same percentage. In the lower part of all the curves, you can see all four curves. When you come towards the lower part, all highways have the same percentage almost. Okay, now what is our job, or why do we plot this type of a graph? Because if you go back, we have studied that if you are calculating your hourly volume for design, then we have to take a dt, and then you multiply with d and you multiply with k. So d is the directional distribution factor and k is this factor which you have plotted on the y-axis. This is k basically. Okay, so k, for some highways k changes, for some highways it is almost a constant. So if it is almost constant, then there is no problem. I can select a value. It's a straight line, I can select a value, no problem for selecting the value of k. What should I do when the graph goes like this? Now if you select the highest value, now remember this represents 1 hour of the year. So if you select, for example, this value 25%, let's say, then you are overestimating. Why? Because this value happens in only 1 hour of the entire year. So out of the thousands of the hour of the entire year, you have just 1 hour in which you have attained a value of 25%. In most of the hours of the year, the value was much less than that. You can see from 25, then it goes to 22%. Okay, now it may seem only 3%, but remember we are multiplying with a dt. So a dt is in thousands. So even if you just change the percentage by 3 or 4%, the value changes by, let's say, 300-400. Okay, so you can see if you select the first hour of the year, then you are overestimating. But if you just go slightly below, so out of the thousands of hours of the year, I am going from 1 to 30, and you can see the percentage changes from 25 to 22%. And if I go towards the 100th hour of the year, again I am just missing out how many hours out of thousands? Only 99 hours. So I am ignoring only top 99 values, and the change in value is only from first to 100. The change in value is only the change in value is 7%. Okay, so just by ignoring few hours of the year, the value of hourly volume, can reduce significantly for these highways. Okay, the highways which are showing this trend, a peak at the start and then going downwards. So normally we select this one. K value is taken for the 30th hour of the year. Okay, so the 30th highest percentage is taken for the entire year to be selected as a K value. Okay, for all types of highways. So obviously if you are talking about these highways, these two, then there is not much difference between the first and the 30th, right? There is not much difference. You can see it's almost the same now. But for the other highways where there is some difference, we go up to 30th. Okay, now you cannot take an average because average will be in the middle. So middle mean you are ignoring half of the hours of the year. Okay, and you cannot take the highest as well. As I said, it will be overestimating. Okay, you are increasing your value by 400-500 vehicles just to incorporate extra 20-30 hours. So it doesn't make any sense. So we try to be close to this portion of the year, the portion which is almost straight. So we try to ignore most of the part of the peak, not most of the part of the curve. We are covering most of the part of the curve from 30th hour onwards. So we are covering the thousands of hours. We're just ignoring most of the part of the peak, which is around 20-30 hours. So in this peak, there are only 20-30 hours which we are ignoring. Okay, so this is how you select the K value. Okay, now this diagram is showing you flow and flow rates. So on a certain highway, flow are taken for 5 minutes period. So you can see each bar is 5 minutes. Okay, and then you see certain small lines here. Each line represents a flow rate for 15 minutes. Okay, a flow rate for 15 minutes. So you take the value for 5 minutes and then you convert it to 15 minutes. So this is what it represents. Okay, and then you see this dotted line. So this line represents the flow rate for 1 hour. Okay, this line represents the flow for 1 hour. Okay, so these are 15 minutes flow rates, these are 5 minutes, the bars are 5 minutes, the small lines are 15 minutes flow rates, and the dotted line is the hourly volume, the flow rate for the entire hour, okay, or the hourly volume itself. Now you can see here, if you can, for example, if you consider 15 minutes value, the 15 minutes flow rate value, so you have taken a 5 minutes value, multiplied by 4, it became 15 minutes, and this is the value. Now you can see within this 15 minutes how much variation we are having. See, even within a period of 15 minutes there is a lot of variation. You see, this value is going down, this value is up, this value is up, and this difference is not small. You can see from here to here the difference is 100, from here to here the difference is 200. Okay, so even in a 15 minutes period we have a lot of variation, and we called it sub-hourly variation. Sub-hourly variation. Okay, so there is a lot of sub-hourly variation here. Okay, and then you can see the variation between the hourly volume and the 15 minutes flow rates as well, and it's a lot. You see, from here to here is more than 400, or yeah, 400. So even the variation between different 15 minutes interval of the same hour is a lot. Okay, so that's why sub-hourly fluctuation has to be taken into account. Okay, and that's why we have the peak hour factor. We have used it earlier as well, and we are going to use it in the other chapters as well. Okay, now this shows curves for different types of highways on different days of the week. Okay, the curve, each curve represents daily traffic on different days of the week, average daily traffic. So how much is the daily traffic for Monday for this highway? This highway means it's a recreation route going to a picnic place or something. And this one is for a rural route, this one is for a suburban freeway, and this is the average of the entire week for all highways. So this is a constant value. Okay, for all highways, so you took the average of all the averages, then you plotted this line, the horizontal line. Okay, so obviously it's for all the highways, so it's just one value. Okay, now you can see for the suburban freeway, okay, the peak is near the weekend. Okay, suburban means you are going towards the boundary of the city. Okay, so the peak is near the weekend, Thursday, Friday. Okay, and if you consider the rural route, then the peak is on the weekend itself. Okay, so there are certain people, maybe they are working in the city and then they go outside. Okay, or people, now why this is higher? Because people may be going to suburban areas to for picnic and for meeting their relatives or friends or something. Okay, so this is why it is higher here. Okay, and same case for what is this is rural route, same case. People may be going outside the city, okay, to different cities or different places, okay, to meet someone, and this is why so obviously they start before the weekend, so they can spend the weekend there, right? They can spend the weekend where they are going. Okay, but if you are going to suburban areas may have picnic places and so on, so then the weekend is higher. Okay, so rural route or recreation route, which one is it? So recreation route obviously higher on weekends, recreation route is higher on weekends, and then for other two routes it is higher near the weekend, not exactly the weekend, near the weekend. Okay, and then you can see on weekend itself, highest traffic recreation, lowest traffic suburban freeway. Okay, so nobody goes, they go to the suburban area near the weekend and then they stay there, till the weekend, they don't come out. Okay, so that's why you have the lowest traffic. Okay, but for this route, which is a rural route, people go near the weekend and maybe some of them come back, so you have some traffic here as well. Okay, some more graphs. Again, percentage of ADT, the K values for different months now, for different months. Okay, so you have two on the first two figures, you have an urban arterial which is solid line, and then you have a summer event influence arterial, an arterial which goes to an area which is influenced by summer. So you can see higher traffic in summer. Okay, you see higher traffic in summer. And urban arterial, almost the same. Okay, almost the same. Okay, here you see, so they maybe it's another urban arterial, so it goes down in summer. Okay, but for the other months of the year, it's almost at, at a very constant level, right here. Okay, same thing here as well. There's not much variation here, and this is what happens in urban areas. This is what happens in urban areas. Then in these two figures, this one is a figure with significant recreational traffic. So obviously it goes up in the summer region, and then you see different lines. Solid line represent weekdays, and dotted line represents, and the other thin line represents weekends. So obviously weekend traffic is higher compared to weekday traffic for the recreation route. Okay, and this one is intercity route. So we have a peak again in the summer, because we have summer vacations, people go out of the city as well, but it doesn't change in different days of the week. Okay, so when summer comes, everybody is going on weekend or weekday, it doesn't matter, they just want to go. Okay, so because they are free. So in all these graphs, what was the purpose of showing all these graphs? The purpose was to emphasize the point which I made earlier, how demand changes. Okay, this is, in all these graphs you have seen variation in demand, variation according to time, according to day, according to type of highway, type of area. Okay, months, seasons. Okay, I have tried to show you all of these in these graphs. Okay, now we come towards intersection volume studies. Now we have already discussed a little bit about volume studies which are done on segments previously as well. We have done some calculations as well. So let us focus on intersection volume studies, and we can move back to the segments as well, or we will discuss some advanced topics in volume studies. So intersections are counted manually most of the times. Why? Because manually, then you can see the direction in which the vehicle is going. If you put a sensor or a detector, the sensor detector can count the number of vehicles, but if you have a driver like me who decides at the end that he wants to take a left turn while he is in the right lane, then detector will not count it accurately, right? The detector cannot count these drivers who take the decision at the last moment accurately. So that's why you prefer to do it manually. Now we have cameras available as well. I have discussed earlier as well that these cameras can be installed with the signal or at a higher place from which you can see the intersection clearly, and then you can record or extract the data from these videos. And there are softwares and algorithms available which can help you record extract the data from these videos. Even when you are counting it manually, you have to position the observer so that his view is not blocked for the vehicles he wants to count. So for example, you have an observer which is standing here. Now obviously this observer can easily count the number of vehicles which are turning right. Okay, but if he tries to count the vehicle which is turning left, then he may have a problem. There may be a big bus here, and this bus may stand there for 2-3 minutes or 20-30 seconds, and it may block the view of the observer. So the position of the observer is very important here. Now when do you count the volume? Volume is normally counted when the vehicles are leaving the intersection, departing the intersection. Departing means, now departing can mean two things. For a straight vehicle, if the vehicle is moving straight, then departing means that when it crosses the stop line, this is the time when it has departed the intersection. Okay, so you will count the vehicle. If you are counting vehicles going straight, you will count the vehicle when it crosses the stop line. For turning vehicles, if we are at a signal, you can still use the same concept or same rule here if you are at a signal. But if you are not at a signal, even at the signals, you can count the turning vehicle when it reaches the other side. So when it reaches here, okay, this is when we say it has departed the intersection. Okay, so for a straight vehicle, departing the intersection means crossing the stop line. For turning vehicle, departing the intersection means reaching the other side. Okay, so the observer, whoever is counting it, he will count from the point when it has departed the intersection. Okay, so if your counting is straight, you will only count the vehicle when it crosses the stop line. Then how many movements you can assign to an observer, because on a signal you have different movements. I have just plotted 2 or 3 in these two sketches here. So you may assign more than one movement to an observer depending upon his skill and experience. Okay, so if he's an inexperienced observer who is new on the job, you should not assign him more than one major movement. Major movement means a movement which has more volume. So obviously all movements do not have the same level of traffic. So if you have one movement which has very high traffic, so you assign only that movement to an inexperienced observer. Okay, because obviously he may not be able to manage vehicles if they are moving simultaneously and if one of them has high traffic. But if there are minor movements, you can assign up to 2 as well to the same observer, even if he is inexperienced, because there are not many vehicles moving, so he has a lot of time to adjust and see from where and in which direction the vehicle is moving. If you have a road or you have an approach on which vehicles are going in different directions and all of these directions have high volume, then you can assign observers to each lane as well. You have discussed in one of the previous topics that if you assign the observer to each lane, then your problem is solved. No matter how high the traffic is, from one lane you will have one vehicle moving at a time, so it will be easier for the observer. So you can do that for heavy traffic approaches. And then you should make sure that the observers are having breaks in their counting period. You can give them short breaks or alternative counting periods, so you can tell them count for 12 minutes, take a break of 3 minutes, something like this. Or you can tell them count for 10 minutes, then have a break for 10 minutes. This is alternative break periods. Okay, and this can also reduce the number of observers, like we have seen one of the previous example earlier, that you can have one observer, for example, counting straight for 10 minutes, then you give 2 minutes break to the same observer, and then you ask him now count straight for the other direction. So same observer is counting for 2 different directions, so number of observers will be less for you. The number of observers you need will be less for you. Okay, so this is a way to manage the resources. Okay, if you have flow which is equal or less than the capacity of the intersection, then counting departure volume is the accurate measure of demand. The volume which is leaving the intersection is the actual demand. But when the demand goes above the capacity, then basically the number of vehicles leaving the intersection are basically equal to the capacity of the intersection. The remaining part of the demand, which is higher than the capacity, is just waiting in the queue. So you may be counting 2000 vehicles going every hour, but the queue behind you keeps on increasing and increasing. Okay, so if you want to get that actual demand when flow is more than the capacity, then you should be observing or estimating the arrival volume. How many vehicles are actually arriving at the intersection, not how many are going. How many are going will be just the capacity then. Okay, so how many are arriving. Now how do I know that flow is more than demand? Okay, now remember I am talking about intersection. So intersection always has some queue. Some vehicles are always waiting at the intersection. So you cannot say if some vehicles are waiting, I have demand over capacity. No, there may be a red signal, there may be a stop sign. Okay, because of that they are waiting. So demand above capacity can be observed or can be ascertained if you have one of these 2 conditions. The first condition is for signalized intersection, the second one is for unsignalized. You can have 2 types of intersections, signalized or unsignalized. On signalized intersections, if vehicles who come during the red phase do not leave in the next green phase, that means demand is over capacity. Vehicles who come during red phase, they cannot leave in the next green phase. Even if some of them cannot leave during the next green phase, this means demand is over capacity. So then you should estimate arrival volume. not focus on departure volume. Arrival volume will be the demand. If you have unsignalized intersection, then there is no red or green phase. Then in that case, you count the vehicles in the queue repetitively few times, and if every time the queue is increasing, that means the demand is over capacity. So you count the number of vehicles in the queue now is 5. After 10 seconds it becomes 7. After 10 more seconds it becomes 10. Then after 10 seconds it becomes 15. So every time the value is increasing. So this is an indication that demand is over capacity on this unsignalized intersection, and then you should estimate arrival volume for the demand. Okay. Now this condition is known as queue buildup condition, unstable queue buildup, because queue keeps on increasing, right? So you call it unstable queue buildup. Okay. So unstable queue buildup is when demand is over capacity. And how do we know it? For signalized intersection, vehicles, some of the vehicles which come during red phase cannot leave in the next green phase. For unsignalized intersection, the queue keeps on getting longer and longer. If you have any of these conditions, then it's unstable queue buildup condition. Departure volume is not the measure of demand. Arrival volume is the measure of demand. Now the problem with arrival volume is you are measuring or counting vehicles which are in the queue, but queue itself is dynamic. Queue moves when signal becomes green, for example, or when there are no vehicles from the other side on a roundabout, then the queue will move forward. So the vehicles which you are trying to count will move forward. Okay, and when the signal becomes red again, or when there are vehicles which are already passing through the intersection, the queue will not remain same. It will increase. So now it is moving backward. Moving backward meaning what? Vehicles are adding to the back of the queue. So the queue was up to this point, signal became red, now more vehicles are adding to the queue, so the queue is moving backward now. So this is the end of the queue now, and the end of the queue will keep on going in this direction until these vehicles have a chance to move. So when vehicles have a chance to move, queue moves forward, and when the vehicles don't have a chance to move because of other traffic or because of the red signal, queue moves backward. So if you try to count the number of vehicles in the queue, the arrival volume, then you will keep on jogging forward and backward. Yeah? So somebody would think that you are doing exercise, you are jogging, or getting ready for Olympics or something. Okay, this is not the case. So it's very difficult to count the arrival volume. So we have come up with an equation to calculate arrival volume using departure volume and number of vehicles in the queue. So departure volume counting is easy. Whenever vehicle passes the stop line or whenever vehicle reaches the other side, you count it. It's easy. There's only one point of counting, one point of observation. So using departure volume and how many vehicles are in the queue at a particular time, okay, not continuously like going backward and forward, at a particular time, like we did for delay studies. So you fix a time, okay, at this time I'll count number of vehicles in the queue, if there are 20 or 30, whatever, and then after this much time I'll count again and again. I will not go forward and backward. Okay, if the queue next minute goes forward, I will stay at my place until the next time comes for counting the number of vehicles in the queue. How do I calculate the arrival volume? Using these two things, using this equation. So VAI, number of vehicles arrived at or during time interval I. So I is the time interval for which you are calculating the arrival volume or arrival flow. VDI, number of vehicles departing during time interval I. Okay, so during same time interval, how many vehicles departed? NQI, number of vehicles in the queue at the end of time period I. Number of vehicles in the queue at the end of time period I. Okay, and number of NQI minus 1, number of vehicles in the queue in the previous time interval. So for example, you fix a time interval of 15 minutes. Okay, or instead of doing this, let me show you with an example. So this is an example. You can see here in the first column, time periods are mentioned. They are 15 minutes. So I want arrival volume for each 15 minutes. For these 15 minute periods, they have counted departure. How many vehicles departed? So between 4 and 4:15, 50 vehicles departed. 4:15 to 4:30, 55 vehicles departed, and so on. Then we have the queue length. This is the queue length at the end of time interval. So at 4:15, the queue length was 0. So when I say queue length, I don't mean the queue length during 4 to 4:15. I mean at 4:15. So queue length is just measured at the end. That's it, one value. So like I said, you don't have to go forward and backward with the queue. Just wait till 4:15 and just count the number of vehicles at that time. That's it in the queue. So at 4:15 0, at 4:30 0, at 4:45 5 vehicles in the queue. Okay. Now how do I calculate number of vehicles arrived? So equation is this one. So I need number of vehicles departed, number of vehicles in the queue now, number of vehicles in the queue previous. Okay. So for 4 to 4:15, number of vehicles departed 50, number of vehicles in the queue now 0, number of vehicles in the queue previous 0. So you get 50, so it's 50. Same thing here. Okay, 55 plus 0 minus 0. Here 62, then number of vehicles in the queue now 5, number of vehicles in the queue previous 0. This one. Okay, so 62 plus 5, 67. This is how we are getting it. And then you can see the same thing here. 65 departed, 10 in the queue now, 5 in the queue previous, and then you get 70. Okay, so what is the logic behind it? What is the logic behind the equation? Logic is very simple. 65 vehicles left, 10 are in the queue, and out of these 10, 5 were already in the queue previously. So how many arrived actually? 65 plus 10 minus 5. So 10 minus 5 basically who are in the queue because of the arrival volume. So 65 who left plus new vehicles in the queue. So that is 10 minus 5. Okay, so you get 70 there. So you can see first two time periods no queue, so arrival equal to departure. So whenever there is no queue now and no queue previous, in the first two time periods there is no queue in the present time interval and no queue in the previous time interval as well. So when you don't have queue now and in the previous time interval, departure equals to arrival. You can see for the first two, this one and this one. Okay. Then whenever the queue becomes 0, the total, okay, I'm talking about the total now. So if you do the total of this column and the total of this column, total of arrival and total of departure, then the total will be equal if at the end you have 0 queue. Okay, so if the final value of the queue is 0, then the total of departure will be equal to total of arrival. I'm talking about the total. Okay, so whenever there is no queue in the present and previous, arrival is equal to departure, and whenever there is 0 queue at the end, total of arrival equals to total of departure. Okay, all vehicles which came they departed, so that's why we have no queue. Okay, if you are doing a counting study at signalized intersection, then you have the advantage that one observer can record more than one movement if they are happening at different times. So you have a different signal for straight and a different signal for left, then obviously a different phase for straight, different phase for left, then you can have one observer which can count straight as well as left without any problem. Okay, because they are not happening at the same time. If you are doing at a signal, then a counting period, selection of counting period is also very important. Okay, so you have one total counting period and then you have one actual counting period. Total counting period is the start and the end of observations, and what time you started, what time you ended. An actual counting period is when you subtract the period of breaks from the total time. That is the actual counting period. So you had a total counting period of 1 hour, and within 1 hour the observers took break for 10 minutes. So the actual counting period is 50 minutes. Okay, both these periods, the total as well as the actual, should be a multiple of the cycle length. Now I've earlier explained cycle length as well. Cycle length means when you have from the start of the red for one phase to the start of the next red for the same phase. This is one cycle. So in other words, when the signal completes all the timings, the red, the green, the yellow, when all timings are completed, this is the entire cycle. Okay, so you can measure from one red to another red. Okay, and so on and so forth. Now why we are saying that the counting period should be a multiple of cycle length. Now multiple means if your cycle length is let's suppose 60 seconds. 60 seconds means 1 minute. So you cannot have a counting period of 4.5 minutes, whether it is total or whether it is actual. Total should be a multiple of 1 minute and actual should also be a multiple of 1 minute. So the example which I was giving is valid. Total counting period 1 hour, so 1 hour is a multiple of 1 minute, and actual counting period is 50 minutes, which is also a multiple of 1 minute. Okay, but let's say if your cycle length was 90 seconds, 90 seconds means 1.5 minutes, 1.5 minutes, then 1 hour is a multiple of cycle length. 1.5 60 is a multiple of 1.5. Okay, so total counting period no problem, but you take a break of 10 minutes, so your actual counting period becomes 50 minutes. So in that case now we have a problem, because 50 is not a multiple of 1.5. Okay, so then actual counting period must be changed, or you change the break. Okay, so why we are doing that, why we are saying that it should be a multiple. Multiple means that you complete the cycles. Multiple means you complete cycles. When one cycle happens, all directions have received their movement time. In one cycle, all directions have received their movement time. So for example, if your cycle length is 90 seconds and you take a counting period of 5 minutes, okay, so in 5 minutes you can have 3 complete cycles. 3 cycles means 4.5 minutes. 90 seconds is 1.5 minutes. So in 5 minutes you can have 3 cycles, and these 3 cycles will be completed in 4.5 minutes, but your counting period is 5 minutes. So what will happen in the remaining 30 seconds? In 4.5 minutes 3 cycles completed, remaining 30 seconds some part of the cycle will be completed. So out of all the directions, maybe one direction will receive green. So in your counting, that direction will show more volume, not because it has actually more volume. It shows more volume because it received one more green time than the other. So all directions receive green time 3 times, and this one particular direction received the extra green time in the remaining 30 seconds as well. So obviously that volume will become higher. So now your counting is disturbed, it's not accurate, it's not showing the actual trend. Okay, so to make sure that all directions have equal number of green times after the end of my counting period, we should take it as a multiple of the cycle length. Okay, now if you have so they are saying that if you have a 60-second cycle length, then a counting period of 4 or 5 minutes can be, can work. If you have actuated signal, now what happens with actuated signal? Actuated means signal is attached to a sensor. Okay, so the observation of the sensor is known as actuation. Okay, so that's why we call it actuated signal, because attached to a sensor observation. Actuated signal timings do not remain the same. So when volume increases, signal timing also increases. So your cycle length is not the same. Okay, so in those cases, counting period should comprise of 5 times of maximum cycle length. So maximum cycle length is usually given by the programmer, the person who designed the signal. So he set this value that whatever happens, the cycle length will not go above this value. Let's say this value is 180 seconds. So now if you are doing observations on an actuated signal, then you cannot take a multiple of cycle length, because the actual cycle length is changing. So you take the multiple of maximum cycle length, which is a fixed value given by the programmer. And how many times? 5 times. So if cycle length is 180 seconds, then total counting period can be 5 into 180, whatever it is now. Now you may question me that what will happen to the extra volume, because the actual cycle length is not 180 seconds. So actually you may be observing 4.5 cycles or 5.25 cycles. Then what will happen to the extra time you give? In actuated signals, signal itself takes care of the side which has more volume. The side which has more volume has already received extra and higher green time. This is the purpose of having it actuated, right? Why are we putting sensors there? So that whichever direction has higher volume should have more green time as well. So in those extra 20-30 seconds which you have at the end, which are not multiple of the actual cycle length, the signal is only giving extra green time to the movement which requires extra green time. So signal is already compensating for the portion of the cycle length which you are counting extra. So for actuated signals, you don't have to worry about the fraction of the cycle length in which a movement may receive extra green time. Only that movement will have extra green time which has already high volume. So the trend is already captured by the signal. Okay, these are different methods to show the volume coming on in different directions of signal. Okay, so you see different boxes here. Each box is representing one movement, and then you see a bigger box which is representing the total volume of that direction. So this direction has a total volume of 400. Out of that, 300 is going straight, 70 is taking left turn, 30 is taking right turn. So the arrows connecting the boxes are showing the movement, and each box is showing the count for each movement, and then you have bigger box showing the total of that approach. And then you see some basic information here, the name of the intersection, date, time, who did the survey, for which city, and so on. This is another notation for showing the volumes or the flows, and we are showing it with arrowheads and tails and with lines. So you see where we are using arrow tail, that means the volume is departing from this direction, so it's going away from this direction. And where we are using the arrowhead, that means the volume is arriving in this direction. Okay, so how many departing from here? 5979. How many arriving here? 7387. Out of these 5979, some are taking left turn. How many? You can see there the line for left turn, and with the line the number is mentioned, 173. Some are going straight, so you see a line for straight, and then you see a number for straight as well, 5540. Some are taking right turns, and you see the number for the right turn, 266 with the line. The lines are showing the movement, arrowheads and tails are showing the total volume of that approach coming and going. Another thing is the size of the arrowhead and tail. It is not selected randomly, it is selected according to the volume. Volume is higher, the arrowhead or tail will be bigger. So this is bigger than this one. Okay, this one with 8000 is bigger than this one because it has more volume. Bigger meaning wider, yeah, like the width is more. Okay, similarly this has the highest width because it has the highest volume. This has the smallest width, where it has the smallest volume. Then you can see the scale is mentioned here as well. We call it the intersection flow diagram. Then for how many hours the count was taken, which hours, and the day and the date is mentioned. This is the notation which they follow in Bahrain. So you can see the boxes are mentioned for different peak hours. There's some basic information given, name of the intersection, date and day, the code given to the count, the date, and the peak hours. What are the peak hours in the morning, peak hour in the afternoon, peak hour in the evening. Okay, and then you can see they are color coded, so each box here with a different color shows a volume of different direction. And then you can see for different movement we are using different boxes. So this is very close to the first example which I showed you, very similar. Okay, so you can see the name of the highways, how much volume for the U-turn, this much. Okay, so this is in the AM peak hour, this is in the PM peak hour, this is in the evening peak hour. How much taking left turn, this much, and again for different peak hours. Okay, so colors of the boxes are showing different peak hours. The box itself is showing different movements, and the movements are indicated with the arrows with the box. Okay.